Welcome to the demonstrator video of the GOP experiment that was conducted during the ECOT project. GOP stands for Generating Optimal Paths and combines two existing methods to create robot motions. This is joint work of Heidelberg University in Germany and the La CNRS in Toulouse, France. Experiment objectives. In this experiment, we designed and tested new algorithms for generating optimal paths for dynamic robots in cluttered environments based on a combination of random search path planning algorithms and optimal control methods. The methods were tested on the humanoid robot HRP2 and an industrial manipulator, the KUKA KR5-6R850. Path planning methods determine collision-free paths in very complex environments. After specification of an initial and goal configuration, path planning tries to find a sequence of postures for the robot that connect initial and goal configurations. La CNRS has long been specialized in efficient planning techniques and their application in robotics. In our experiment, we use methods based on rapidly exploring random trees. This sampling-based approach explores efficiently the configuration space and allows to perform path planning in an efficient manner. As this is done randomly, the resulting paths are not necessarily intuitive or efficient. Optimal control methods are capable to generate trajectories that take the robot dynamics into account. They optimize infinite dimensional functions and thus need special treatment when solving numerically. Efficient algorithms for the solution of optimal control problems have been developed in Heidelberg. We use a direct multiple shooting method to solve the optimal control problems. Depending on the problem formulation, the motions obtained by this approach are both efficient and natural looking. However, treatment of complex environments is very difficult to handle. Furthermore, constraints have to be piecewise continuously differentiable. Achieved results. By inserting the robot dynamic model equations in the optimal control formulation, physical constraints such as balance can be enforced. In this project, we created a framework that combines path planning and optimal control methods. The path planner computes an initial collision-free path, which is then refined by the optimal control solver. The collision detection facilities that are available in the path planner are called from the optimal control solver to check for collisions. The environment and geometric properties of the robot thus have only to be specified once for the path planner. Dynamic parameters of the robot are used in the optimal control solver to compute trajectories that exploit the robot dynamics. Additional constraints are specified in the optimal control solver, such as joint torque limits and velocity limits, and so on. Furthermore, we add collision avoidance constraints, which are based on capsule models. Capsules are generated automatically for each robot body and allow fast distance computations. Using capsules, distances are piecewise continuously differentiable and thus suitable for optimal control methods. In this ECOT experiment, we established software that combines path planning and optimal control methods. The motions generated are smooth and collision-free for a wide range of robots and thus make it ideal for service and medical robots. Experiment demos. In demonstrator 1, the KUKA bartender robot, we generated motions for the KR5-6R850 robot arm. It has 6 degrees of freedom and a maximum reach distance of 850 mm. It is equipped with a shunt gripper and a custom glass holder. The aim of our demonstrator is to swiftly move a glass with liquid in a complex environment without spilling the liquid and without self-collisions or collisions with the environment. To achieve this, we minimize accelerations of the glass along its local sideways axis and require a minimum acceleration along its vertical axis. Additionally, the motion is minimized with respect to time. There are two scenarios. In the first scenario, we move the glass from a high position to a low position. A direct path is not possible and would lead to collisions with the environment. In the second scenario, we move the glass from one side to another. HRP2 is a humanoid biped robot with 30 actuators, which makes it a highly redundant and versatile system. In our scenario, the sum of square jerks is minimized to produce smooth trajectories. Constraints on joint limits, dynamic balance, and collision avoidance are added in the optimal control formulation. In this scenario, HRP2 must grab a ball in the lower shelf and place it on the higher shelf while remaining balanced and avoiding collisions with the obstacles and itself. A draft collision-free path is first found with the path planner. It is then used as an initial guess by the optimal control solver to generate a smooth, feasible, collision-free trajectory. The trajectory was successfully replayed on the real robot.